guess to start off, Jacob, would love to hear more about, who you are, particularly where you grew up and what your journey was to ultimately pursuing science and ultimately getting your PhD at UCSF.
Yeah, sure. So I grew up in a small town in Florida. It's called Satellite Beach. There is not a lot going on there, to say the least. I first got interested in science, honestly, by a stroke of random luck. Through circumstances I don't totally understand, my high school had a bunch of very sophisticated lab equipment donated. So we had hundreds of thousands of dollars of cell and molecular biology equipment, but no one knew how to use it. And in retrospect, it was kind of funny. We would often, stop doing experiments for the want of like $100 bottle of some reagent. But because we had this equipment, we oddly enough had a class where basically the entire purpose was to go into this lab and try and do some experiments. There was no agenda. Everyone was doing something different. It was just called science as like the course title, which was kind of amazing. I honestly think it changed the course of my life. And that's how I got oriented toward biology. I sort of always knew I wanted to be a scientist. I've always been interested in building things, shaping the world around me, understanding how it works. And that's really how I got keyed into biology in particular. The only other salient thing here, I often get asked, like, why work on aging biology? And it's funny, I almost never thought of working on anything else. Very briefly when I was young, I wanted to be a physicist. And I thought, Niels Bohr showing the quantum state of matter was the most beautiful experiment ever. And I was kind of bummed out because it seemed like all the important stuff in physics had happened like 100 years ago. You read the textbook and all the years are just really far back and you're wondering why there aren't more recent ones. And then I came to start working in this biology lab and trying to learn more biology, and I started reading a textbook. And it starts out sort of in the format almost of a novel with here is how life begins, and then starts describing how everything works. And in this beginning chapter, they have all these details about how you go from a single cell after an egg and a sperm meet all the way to an animal. There are all these beautiful descriptions of exactly how this happens. And I just kind of figured like the end of the story would be the parallel to that. Here's why everything beautiful will one day decay and die. Here's how aging works. And then there was just kind of nothing. The book just ended. And at first I figured I must just have a bad textbook. James Watson must not know what he's doing. And so went and tried to figure out why things all aged. That just seemed like a logical conclusion to the story, and realized this was basically an unknown problem in biology. And so really ever since I've been working on biology, since the time I was a teenager, I've sort of found this the most fascinating question and the one that I think has some of the highest potential impact of anything in biology. So that's sort of how I got started working in science. My first ever like formal job in science, I was an intern at the National Institute on Aging, which sounds very cool. The actual job I was doing was clicking on pictures of worms all day, identifying their various body parts. I used to dream of worms at night. But nonetheless, it started giving me a passion for asking some of these very fundamental questions using computation in a way that we couldn't before. The basic sort of task we were trying to look at was, do different organs in this worm age at different rates? Like, does the heart age faster than the brain? And it turns out it's actually kind of tricky to answer. And this was one way of doing it. So I've been sort of on that track for a while. I eventually did an internship at UCSF at one point while I was in college. And I had grown up reading Paul Graham's essays and like trolling Hacker News from the middle of nowhere in a small town, really inspired by people building institutions rather than just joining existing ones. And I'd always imagined the Bay Area would be a place I'd love. And then I was here for like a week and realized that I had to move here. This was the place where I felt the most at home. So then when I went to graduate school, I interviewed all over the place. I was sort of choosing between Harvard and UCSF. And then it just became obvious to me, like I knew I wanted to be in the Bay Area and not in Boston. And so that's sort of how I ended up at UCSF. And it just so happened to have one of probably the 3 or 4 best communities of aging biologists in the world at the time. So I continued to pursue my PhD there. So hopefully that gives you a bit of the background vignette with some of the lead-in, and then also how I got into actually doing the science for real.
Yeah, absolutely. I'm curious. I've heard from, peers who've pursued PhD programs that sometimes going into business or startups or tech instead of continuing like academia and research is looked down upon in some ways. And it sounds like you've always had an interest in that, but I'm curious if that was ever a question in your mind about whether you'd, pursue something different after you graduated.
Yeah, no, that's absolutely true. It's funny. I came into academic science really inspired by entrepreneurship and company building as a vehicle to deploy ideas out into the world. But then once you're in an academic setting, it's almost hard to describe to an outsider how it can start to feel to you. But imagine that every single person that you look up to, who you interact with on a regular basis, has spent their whole career in the academy. And they define success in terms of things that are recognized within the academy. Even if someone is not actively disparaging alternative paths you may take in life, which is the majority of paths one might take in life, can start to feel as if all other possible paths are in some way failure. And so certainly there was a time in my academic career, even when I was, finishing my PhD and choosing what to do next, where it felt like to me in some way anything other than trying to be a professor was admitting defeat, admitting that I couldn't win at the academic game rather than, truly deciding not to play. And so that definitely was a feeling in the back of my mind. I feel very fortunate that I did have enough interaction with people outside of the academic setting and enough really open-minded advisors that I was able to make the choice to go into an industry setting where I think the things I've been able to do in terms of my career have been far outweigh what would have been possible in the counterfactual. But it definitely was a difficult emotional decision, even for someone who came in wanting to pursue an industry career at the outset. And I think this is a pretty common story you'll hear from people in similar situations.
Do you have any advice for, Jacob Juniors who are doing their PhD program, who are feeling the same and are trying to figure out is there a reason why everyone seems to be disparaging this kind of alternative path? And then I guess on the other end of the spectrum, curious for any advice you have for the PhD programs themselves, or if there is anything they can do, or it's just too institutionalized to kind of think through that this, academic path is the right one. And that's kind of how they're built against as well.
Yeah, both great questions. So I'd say if someone is interested in exploring alternative careers, my best advice that I give quite often seems fairly quotidian, but you'd be surprised how seldom it's taken, is honestly just to seek out people who are in alternative career paths and then try and have a conversation with them. Especially people who are relatively early in their career, people who just left their PhD, will often be relatively flattered that you're reaching out to them and want to talk to them about their own life trajectory. And so I think a lot of PhD students underestimate how easy it is to have a conversation with someone who has real world experience. I think a lot of the reason that this emotional drive to continue in academia builds up is simply that everyone you speak with, everyone who forms your social community, is pursuing that same goal. And so broadening your network to include people who are pursuing a more diverse set of goals, not necessarily spending every hour in the lab at the university, but occasionally taking one to have coffee across the street with someone building a business or pursuing a nonprofit or doing honestly anything different, I think can help break down some of that emotional barrier that stands between you and choosing to pursue a different goal than everyone you interact with is pursuing at the same time. And then to your point on PhD programs themselves, I definitely think that there's sort of two places where someone can optimize if they're interested in maybe pursuing an industry career. One is on the front end when you select a program. That's not very helpful advice if somebody's already in a program, but there are programs that are in locations where you'll have a lot more exposure to the industry. I think in biotech, this tends to be the Bay Area, Boston, San Diego, Seattle to some degree. And I think a lot of those programs even have to some degree formalization around doing internships with companies and having relationships with a corporate organization while you're in your PhD program. And I think all of that is strongly advantageous to if you're interested in pursuing an academic or an industry career than just a purely academic path of being in a relatively isolated situation. The other thing I encourage everyone to do is to try and do an internship in industry, even if you don't really feel like it's for you, even if you feel like you're set on the academic path. And the funny reason is that, when you finish your PhD, you can get all the way to the end of your PhD and have never had a job outside of academia. And so you can end up being almost a fully formed adult and yet never having sampled anything outside that distribution. And so I encourage everyone to at least get exposure to it. Maybe it's just going to reify your decision that you really want to be a professor. But I think for a surprising number of people, it demystifies the experience to them and shows that a lot of the preconceptions they have about what doing science outside an academic setting would be like are quite false.
Interesting. I guess leading back to your own journey to industry, what did that look like? So were you proactive in meeting people and you were kind of figuring out where to join? Or I imagine the programs were swarmed with recruiters, like investment banking recruiters for MBAs, for example. I'm sure it seemed like a more proactive thing that you had to seek out.
Yeah, definitely. It is funny, especially relative to the technology industry, where a lot of these early career opportunities prior to graduation and undergrad, in the case of CS as an example, are relatively formal. There are these big internship programs you go join. There are these big recruiting fairs. In biotech industry, that's actually not really the case. It's not as mature of a market. And so I realized about a year and a half into being a PhD student that I didn't want to be an academic. There was a day where it sort of triggered in my brain that the things I really care about are impacting people in the real world. And I think academia is the best place to answer fundamental questions, but what if you're really trying to measure as your milestone or the number of ill patients who are healthier as a result of your work, that industry was probably the more salient place to apply your efforts. And so after making that decision, there was just like a day where it happened for me. I recognized that probably the highest leverage thing to do was to try and gain exposure to people working in different settings and to try and work in one myself. So I ended up doing an internship at IBM Research down in Almaden, right outside San Jose, which was a pretty amazing introductory experience to what doing even relatively fundamental science in industry could be like. And then eventually I got connected to a number of people who worked at different companies. Largely this was just connecting with people through alumni networks or through mentors I already had, having connections to other mentors, all the usual ways one goes about meeting impressive people in the world. And that's actually what ended up leading to the job I took right after PhD when I went to a company called Calico.
Very cool. Yeah, you were there for almost 4 years, so like clearly made a big impact there. Maybe tell us a little bit about it, set the stage a bit of, how big was the team when you had joined? What was kind of the mission of in your day-to-day, like when you first joined versus, what you accomplished as a team or even personally learned over those 4 years?
Yeah, sure. Yeah, so Calico is a really amazing organization in terms of doing some of the best science I think you can do in the world. So when I first joined, I want to say my employee number was something like 139. So there was some level of turnover. So I want to say there's probably 120 something employees, definitely under Dunbar's number. Everyone knew everyone else. And I think that it made for a really amazing environment where even though the organization was large enough to have an impact, it was also small enough that there was very little communication friction. And so I really do feel like I learned a tremendous amount even just in that first year. When I first joined, I was working largely on some oncology programs, working as part of a team to develop new computational tools to advance those medicines. And I think for me, that was also a big learning curve, recognizing or trying to understand how team science was practiced as opposed to an individual mindset. The funny thing about academia is that it's actually just very different than working in almost any other setting. You sort of pride yourself on doing things basically by yourself, not coordinating with anyone else, not really learning to work well with others. The more you do on your own, the better you are. And it turns out to actually accomplish hard goals in life, you want to really skew the opposite way that every other industry recognizes. You want to learn to collaborate and work with others, get more done together as a team than you could alone. And so I spent a lot of time learning to do that through that team. I originally joined a team that was founded by Daphne Kohler, who later went on to found a company called Incitro. And that was probably about 20 people, a lot of whom were data scientists, machine learning scientists who were approaching biology from the first time. I think another big lesson that came for me was that the way they would approach problems was often quite distinct from the traditional way a biologist would learn to approach one. The questions they asked were just simply different. Not always better, but different enough that by combining those two lenses, you often got somewhere that you wouldn't alone. So I worked as part of that team for a couple of years, and eventually that transitioned into I started running an independent group. And a lot of the questions I was working on there were more oriented toward asking how cell identity programs influenced aging. So it's sort of a highfalutin way of saying, do the different cell types in your body age the same way? Does your tongue age the same way as your kidney? It might feel like the answer to that should be obvious, but it turns out that when we set out to ask this question, there actually was very little evidence you could point to in any hard and fast way to make a claim. And so I spent a lot of time working at the intersection of functional genomics and ML tools to try and answer questions like this. So we performed studies where we were able to show that different cell types in your body actually do age in very unique ways. Your kidney does age differently than your lung and your immune system. And while it may seem quotidian, that hadn't actually been appreciated before. And then once we recognized that, we started to ask some questions about the causal direction of that biology. Does the identity program, the type of cell the cell is chosen to be, does that influence how it ages? And could we manipulate those identity programs as a way of maybe changing the cell's age, so to speak? And so we first explored this a bit in some natural systems where cells change their identity. So it turns out stem cells do this naturally. It starts as a stem cell where its mission in life is to grow and make sure you can keep making more cells. And then as it's presented with a challenge, it becomes an adult cell that really does its job. And we found that during those transitions from those stem cells to those adult cells, often features of aging that emerged in the stem cell were resolved. They were reversed through that process. And so this is kind of a really amazing natural example where a cell engaged a bunch of these identity programs and was able to change its age, so to speak. So that got us interested in sort of the obvious next follow-up question, which was, could we do this artificially, not endogenously using biology as it might exist naturally, but could we take some of these programs and activate them in a way where we're specifically trying to reverse the age of a cell? And the science here can get a little complex, but the short version is that all the cells in your body have the same DNA, and yet they do very, very different things. That's kind of surprising when you think about it. How does that happen? They've got the same code. How are they all executing different programs? And it turns out there's this layer of regulation on top of DNA called the epigenome. It's a bunch of chemical modifications. They basically tell your cells which genes to use at which times. And it turns out that can get messed up with aging. So your cells stop using the right genes at the right time, start using the wrong genes at the wrong time, and that means they perform their functions worse, and then diseases can develop. And so we got really interested in the idea of trying to use some of the molecules that coordinate those epigenetic marks that actually change which genes cells are using as a way of reversing these features of aging. And so that broad approach is known as epigenetic reprogramming, which is sort of a great piece of biology branding. And in practice, what it means is we're manipulating these genes called transcription factors. They're sort of like conductors in an orchestra. They don't really do much work themselves. They just kind of go around and tell other genes what to do. You play now, you don't play now, you turn on, you turn off. And just by manipulating these transcription factors, we thought perhaps you could make these old cells look young in terms of the genes they're using. So we built some systems that allowed us to test many combinations of these transcription factors experimentally. What if we turned them on in these old cells? And then we built some ML tools that would let us measure the genomic profiles of these cells and ask, did it make the cell look younger? And it turned out the answer to some of those questions was, surprisingly yes, that you could find these combinations of relatively small numbers of genes that could make an old cell look young. And we got very excited by this, and I think it really could unlock a new therapeutic modality. And that's really what we've been working on at New Limit, is sort of taking that biology forward and trying to build medicines from it.
As you think about like the frameworks when you're approaching one of these problems, I mean, you mentioned a couple things like, you observe different parts of the body against each other. You're observing, the part of the body over time. You could observe things in nature. I forgot what animal it is, but there's one animal that I guess doesn't age, but only dies through like various diseases. And so you could kind of think about that as like a methodology, or at least that's what kind of Scientific American headline about that animal is. And so like, as you're kind of starting to approach one of these really problems, like, is it just really, really, really smart guessing and checking, or how do you kind of apply the right frameworks that will kind of maximize your shot and time and opportunity when you're trying to think through one of these problems?
Yeah, no, it's a great question. And I think this is something that's actually under discussed in science, like ways to frame a problem. I think the classical way of framing one of these problems in molecular biology is to try and find a single molecule that you believe controls a pretty complex process. And the goal of many molecular biologists, since really the golden age of molecular biology in the 1950s, has been to find a molecule, find something very specific it does, and then give it a name. And you can tell this nice linear story of thing X does thing Y and leads to thing Z. It turns out that a lot of biology is just more complicated than that. It's not like there's a box full of widgets and each widget does its own individual thing. The widgets all interact. A lot of the properties of biology you come to know and love, like the ability for us to have this conversation, are many, many widgets interacting in interesting ways. And those same widgets can do other things in other contexts. And so I think that would be the traditional framework for trying to find, for instance, an intervention that makes old cells young, would be to ask, is there a single molecule I can manipulate? Is there, for instance, a gene that increases in expression with age a lot? And maybe if I turn it back down, that'll make the old cells act young. And you would then go and interrogate that hypothesis in some model system. And so I guess one way I try and frame a lot of these problems is to ask not, what is, quote unquote, the right hypothesis? What is the one molecule I should go after? But what is a way I can set up a system where I can test many different ideas and know in a relatively unambiguous way whether any of them has proven successful by some criterion? Mm-hmm. Maybe one way I like to frame it is that, in machine learning, there's often a tension between working on building interesting, fancy new models and then working on building interesting, fancy new objective functions. Mm-hmm. Like, what is it that I'm trying to get my model to do? Mm-hmm. And then what is the model I'm trying to optimize? Mm-hmm. And biology is honestly not all that different. You can think of our models are built out of atoms. They're not built out of bits and weights, but we're setting up some experimental system that hopefully achieves an outcome. And I guess the framework I try and use the most is really defining the objective function well, and then setting up an objective function where you actually have the ability to get many shots on goal. So I'll just give like one concrete example of this from a framework perspective. If you're presented with two ideas for how to make an aging organism healthier, one of them might be something like, well, we've observed this organism out in the wild tends to live longer than this closely related organism, and it has a bunch of genes that are different. We don't really have a clear way of testing that complex intervention, but we're going to make a bet that it's this one gene. And we're going to do some sort of experiment where we introduce that one gene from the long-lived organism to the short-lived organism, and then we're going to wait and measure its lifespan. And it turns out an experiment like that can be really powerful if and only if you're right.
Mhm,
But it also
right.
takes a long time. The thing you're measuring might be like multiple years of an organism's life. There's a really high probability that you don't actually learn anything because maybe nothing happens at all. And all you've learned is that, well, this gene isn't in and of itself sufficient to make lifespan extend. Is it part of the story? Still unclear. And experiments like that, I'd say, are really potentially high risk, high reward, but don't offer a lot of room for iteration or improvement. An alternative might be to say you've got a hypothesis that there's a specific type of cell that is causing a disease. This cell gets crummy as you get older. And maybe there are some ways I can poke it or interrogate it and determine if restoring function in this cell would actually benefit the organism writ large. And it turns out that in biology, the experimental systems you might be able to use there allow you to get many more shots on goal. And so in some ways, it's a more limited question. You wouldn't necessarily be able to measure this ultimate outcome of the organism living longer in a really exciting way. But you're going to have a lot more opportunities to try and actually test diverse hypotheses and be less dependent on just being clever up front. So those are a few of the frameworks that I have in mind when I'm thinking about an experiment is like, what's the throughput of this? How many hypotheses can I test? What's the objective function? How unambiguous is it if something works or not? Does it give me clarity around whether something is necessary or sufficient or both? And then finally, a third one would be, what's the sort of level of impact if I'm right about this particular question? Because there are a lot of things in biology you can explore that are maybe interesting, but if you do the thought experiment where you just quote unquote know the answer, it actually is a little bit hard in your mind to connect the dots to why that's important. Totally. And so that's sort of the third question that's important to ask that I feel is sometimes underweighted in academic training. You're often taught to really emphasize, well, this is important because it's new. And I think industry is great in sort of training you the other way, where this needs to be important because there's some application of it, if I'm right.
Interesting. I guess it's a good segue into learning more about New Limit. And I guess maybe just to start, would love to hear about what is New Limit actually doing, I guess, in layman's terms today.
Yeah, sure. So New Limit's pursuing a bit of the biology we described earlier, called epigenetic reprogramming. Our overall mission is to add healthy years to each one of our lives. So we boldly say we are trying to extend human health span. In a funny way, I think we're really just saying the quiet part out loud. That's really the mission of most drug discovery firms, but we want to make it front and center. Like that is actually the goal, to add healthy years to your life, and we want to forecast that ambition wide. So the idea here would be to say, given that we know that these epigenetic changes can contribute toward age-related dysfunction, and we actually do know it's possible to reverse those changes, which is kind of a really amazing result to think about. We actually know it's impossible to reverse features of aging. And we know it's possible to do that using this mechanism of changing a cell's identity and its age at the same time. Can we find ways to change just a cell's age without changing its identity? And so maybe I'll unpack that a little bit. We know you can take an old cell from an old mouse that's on death's door, and you can change it back into a stem cell just by manipulating 4 transcription factor genes. It's kind of remarkable to think about. There's tens of thousands of genes in the organism. There's hundreds of thousands of different biomolecules, and you can turn on just 4 things and take this old cell back to a young stem cell-like state. That was rightfully rewarded in 2006 with the Nobel Prize. And it turns out when you do that, you're changing not only the cell's type, but also its age. If you then take that cell, you can generate a young mouse with a full life ahead of it. And so again, it's a little bit mind-boggling, but this old cell that had been alive for years in this animal that was about to die can be reprogrammed all the way back and then give rise to a whole new animal that lives a normal life. And it turns out you can do that on a loop. People have actually done that 13 times in a row. And I think they stopped because they got bored. At that point, if you multiply out, it's like a 30-year experiment. I don't think they stopped because it stopped working. And so we have this existence proof. We know we can reverse many features of aging using this mechanism. So if we know all this, why aren't we doing it today? And the basic answer is that that process is changing, again, not only the age, but the type of a cell. We're turning an adult cell back into a stem cell. And if we tried to do that in a body, it would actually be quite detrimental. Your cells would forget what job they're supposed to do, and bad things would happen. So our question then is, can we try and preserve some of that reversal of age while not necessarily changing cell type? Again, we know that the former is possible, changing both together. What we don't know is if the latter is possible. So to your point about frameworks, Lior, I think the way we've tried to conceptualize this is by asking, are there tools we can set up that will allow us to interrogate a large number of hypotheses about how to change cell age without changing cell type? How can we find a set of these transcription factors that might mimic that former miracle in a new cell type in a disease setting? So we're building a number of functional genomics screening tools, which is, again, a bunch of great branding from biology, which is to say, we use genomics as a way to perform many experiments in a single dish. Rather than having one test tube per hypothesis, we have one dish of cells, And we use DNA barcodes to actually encode the logic of our experiment in nucleic acids rather than in physical space. You can then deliver a whole bunch of transcription factors to cells in this dish all at once. And the randomness of biology means that every cell will get a slightly different combination of these transcription factors. And then we can use genomics to read out what happened to those cells. Do they look younger after you've perturbed them? Do they express young genes again? Have the old genes turned off? These are obviously simplifications, but I think give you the general idea. And that's the sort of experimental paradigm we've been working with. And I think an important thing to call out is that even if we were the best people in the world at that by an order of magnitude, we still would never be able to test all of the transcription factor combinations. There are just too many. For the computer scientists, this is something that quite readily becomes apparent when you just say the word combination. There are only about 2,000 transcription factors in the human genome, but if you imagine you might need a combination up to 4, the number of possible combinations is more than stars in the universe, grains of sand on the beach, etc. You're never going to be able to test them all. And so in parallel to being able to build these experimental tools that allow us to search through many combinations, we're also building ML models that allow us to predict what will happen when this unseen combination of transcription factors is invoked within these cells. And I think a sort of nice feature of this setup is that the models don't actually have to be perfect. We don't have to get the exact right answer. We just have to be able to rank order which of the hypotheses are the most interesting to go out and explore. So those are the sorts of tools we've been building in order to ask this question. And now I think an important follow-up would be, okay, let's imagine we're successful. We have all these wonderful genomic screens. We have all of these wonderful ML models. We found some transcription factors that make an old cell look young. What cell do you want to go after? And how does that help a person in a concrete way? How do you make that into a medicine? And so the downstream portion of what we're working on are developing medicines for a few age-related diseases. We're starting an immune system with T cells of your immune system that lose function as you age. So when they encounter a new pathogen when you're 25, they respond very vigorously. You get the flu and it's kind of annoying, but it's not much of a big deal. Unfortunately, by the time you're 70, your chance of an infection like that killing you goes up by 200 to 300-fold, depending on exactly how you measure it. So we are trying to restore function in the aged immune system to actually bend that curve and hopefully be able to give an elderly person the same responsiveness a young one would. So the way we would imagine delivering a medicine like this actually piggybacks on some technology a lot of us are familiar with now from the COVID vaccines. But just 10 years ago, you wouldn't have really been able to deliver reprogramming factors to cells, even if you knew what you wanted to deliver. You wouldn't be able to get them in there and actually make a medicine out of it. But now, thanks to mRNA technology and lipid nanoparticles that can deliver these mRNAs encoding reprogramming factors to cells, there's actually a tractable way to take that answer to this search problem and try and turn it into an impactful medicine. That's just the first of the types of products we're hoping to build, but hopefully gives you a more concrete idea of how would all of this basic scientific work actually result in something really valuable for society.
If one of the core limiting factors at the moment is computation, talk about that as a change and inflection here, because I think some people still would associate biology with most of the work being done in the physical world, when to your point, a lot more of it's getting done in the computational world. So maybe talk a little bit about some of those changes and kind of what you're observing as to like what we can simulate and what you think we will be able to.
Yeah, sure. It's a great question. So this is one of my underlying theses for how biotech will change over the coming years. It's funny, actually. There's a new neologism that at first I disliked, but I've come to have some endearment for. Is called tech bio. People just invert the acronym, and I think what those two different names actually connotate, or what the core competencies of those types of companies are. So traditional biotech, I'd argue, really has a core competency in manipulating atoms in the physical world. They can make a medicine that might be hard for someone else to make, even if both of them knew what goal they were going after. We're trying to inhibit molecule X. Our traditional biotech probably has some clever way of inhibiting X better than their competitor does. Whereas I think in the tech bio domain, so to speak, really the core competencies of a lot of these firms are manipulating information in a new way. So you're either learning which experiments to do more rapidly than you would in the alternative case, or you're learning which types of targets to go after and how you might approach them in a way that's distinct. It's not necessarily that you're better at moving atoms around, but you're better at moving bits around is one way of framing it. So I think that's overarching a way the industry is changing over time. I think there are still some problems where computation is not going to be the one-stop solution. But there are many of these traditional drug discovery problems where I imagine if you can make better decisions up front about what experiments to do by relying less on your intuitions and more on the data we've accumulated, you can start to accelerate the process. So for us, one example here would be that in the past, the number of transcription factor combinations we might have been able to explore would have been only in the tens. So just to give you a concrete example, in this field of partial reprogramming, trying to change cell age without changing cell type, the total number of factor sets people had tested prior to an organization like New Limit was about 19, whereas we do hundreds in an individual experiment. And part of the reason there is that both on the input of knowing which factors should we test, and then on the output, knowing when we perturb cells with these factors, did it actually work, quote unquote? Did we make an old cell look young? Without relatively sophisticated computational tools, you're not able to do that at scale. You're relying on individuals to make those decisions on a relatively one-off basis, and that actually becomes rate limiting. So I'd say another set of problems that's interesting that emerges here is that we can often crib from advances in computer science and other domains to benefit biology. You can take tools that have been developed for computer vision or natural language processing and translate them quite readily. But I think we're now actually entering an era too, where there are a certain set of problems that are unique to biology. There are things like physical constraints on the types of experiments you can run next, as an example. That's one that comes up often for us, where there aren't really even established algorithmic approaches to be able to take a bunch of predictions and figure out, given the physical constraints of which of these experiments can be run together and which can't be run together, what's the optimal set to do next. And so I think we're actually transitioning through a period where perhaps the first epoch of sort of bringing ML into bio was just adopting methods wholesale, to where we really do need to develop some new methods and approaches to be able to address these specific questions in drug discovery. So that's a very broad, airy sketch of sort of how I see the field and the intersection, but hopefully provides some insight.
Super interesting. Lots of follow-up questions, but I guess even just jumping back to, forming New Limit and co-founding the company, you guys have a very interesting story, a very interesting co-founding team even. I'd love to hear more about, what made you decide to start New Limit to begin with, and how did that initial team form?
Yeah, sure. So I think if I'm going chronologically, the movie actually starts before my character is introduced. So I think chronologically, what happened here was Brian and Blake, two of my co-founders, Brian Armstrong, CEO of Coinbase, and Blake Byers, who's formerly a general partner at GV, were very interested in this biology, partial reprogramming biology. And I think the actual inceptive moment was something like Brian told Blake he really wanted to work on a health span extending company. And Blake will joke that, he told Brian that was a terrible idea. And that, actually there already was a company, it was called Calico, and it was already on the case. And then they came to learn about this new biology and recognized that it was distinct enough that a dedicated organization might actually help accelerate the field. And so I had done some research in the field. We got connected with some mutual friends. We started talking about what the possibilities for this biology were, the number of potential applications of these tools. And I think we all came to agree that we could accelerate the pace of discovery in this field by having a dedicated organization. There were a sufficient number of problems that had been reduced from science to engineering, where really we knew what we wanted to do tomorrow. The challenges were more in implementation and execution than they were in the very fundamental discovery portion. That building a company around this idea could actually increase the pace of what the sorts of medicines that we might be able to develop. So that's really how New Limit came together. I then roped in our fourth co-founder, Greg Johnson, a friend of mine I had worked with for a number of years, who at the time was doing exciting machine learning work up at AWS. But we managed to rope him back into biology, where the problems move slower, but are potentially much more rewarding when you come to the end. And that's sort of how the company got nucleated.
Oh, wow. Very cool. And I'm just curious, actually, you obviously, you've been a researcher and, you're an expert in terms of the science behind everything, but what has it been like becoming like a co-founder for the first time? Has your day-to-day been impacted much? Or I'm kind of curious about.
Oh boy, yeah. I move a lot. I move a lot more desks than I used to. That's what I came into the office and did this morning. I put a desk together and packed it somewhere. It definitely has changed where I spend my time. I think as a scientist, you advance in your career by being a technical expert. I don't think it's actually all that different than being a software engineer, where for the first phase of your career, really the way that you move between levels of scope and impact is by developing new technical skills. You get better at solving hard problems. And then at a certain phase, it turns out that even the best individuals cap out on the level of scope they can achieve through pure technical impact alone. There are some problems that are just hard enough that you need to coordinate multiple people around them rather than being the cleverest one in the room yourself. And so I think for me, in terms of day to day, that's been the biggest change is that I spend a lot more of my time trying to recruit, empower, and provide resources to really talented technical experts. And very rarely am I actually the technical expert on a problem when we're sitting in a room together. And so I think that's been the most dramatic change. And it is, to some degree, a jarring experience. I think something that a lot of folks go through when starting a company, again, regardless of whether it's science or more engineering oriented, is to recognize that actually it can become an active impediment when you try and dig too deep into the technical details. So that has definitely changed my day to day. I think the types of problems I think about and the types of time spans I think about have also changed quite dramatically. I think as an individual, even running a lab, I was often thinking about the completion of the next project, the publication of the next paper, maybe the next milestone of the development of a molecule. But when you think about trying to build a company that hopefully will last decades, I think the types of challenges that you try to predict, whether or not you can is maybe another question, but the types of challenges you try to predict down the road almost increase in timescale by an order of magnitude. We now worry about things that might not become a salient problem for many years. That's something that I didn't have a lot of actual experience doing prior.
Interesting.
Given that Brian is, so there's obviously been a lot of examples of companies in which, there was a chairman or chairman-like figure or kind of co-founder that had other things to do, like figure, whether it's, Oscar Health or Tesla or Varda or Anduril. I mean, there's a lot of really successful companies that have had this kind of situation. As the co-founder who's full-time, obviously working on New Limit, like, how do you think about that relationship and how do you best leverage that other person, given that it's not like it's a non-traditional situation?
Yeah, no, I think it's a great question. And one way I like to think about this is that Brian, in many ways, Brian and Blake both are perfect complements to the things I am good at and not good at. So things that I do not have or did not have a tremendous amount of experience at coming into New Limit are things like building a company from scratch, learning how to run a recruiting organization, learning how to operate an organization and set the operating cadence for that business, learning how to make key decisions that have very large financial scope. All of those things are second nature to some of my co-founders who have been doing them for quite a long time, even if the science itself is new. And so I think in that way, we have a system where we're able to defer to each other on our regions of expertise, and they're relatively non-overlapping. And that means that I think together we end up making better decisions than any one of us would have alone on this relatively complex problem. And I feel very privileged to be able to work with both of them to make some of those operating decisions that, quite honestly, otherwise I'd just be bumbling my way through and probably we wouldn't have been as successful as an organization.
Are you guys still, or do you guys still not have a CEO? Which I had read, I think, back in like your May announcement, or have you guys? Oh, that's awesome. Is that challenging at all, or is that just something that you guys are going to
it honestly hasn't been challenging. It's a little bit funny, but there has not been a situation where we felt like having a person without this title at the company has become an active impediment. Again, sort of the way we've made decisions, I think, often relies on deferring to each person's region of expertise. And maybe with a different cohort of co-founders who had different epistatic interactions, that might lead to more tension. But given the organization we have today, I think there's often a pretty clear decision maker for each given problem we run into. And that means that it really hasn't been much of a challenge. I think we've managed to function better together than maybe we would have in some alternative model.
Very cool. I was also curious, I guess, maybe kind of going off this conversation of how you guys formed as a group. I think Leora and I have a lot of peers, for example, who, aspire to be founders or are founders and want to work on kind of more scientific or deep tech problems, but don't necessarily have the background themselves, but are kind of willing to ramp up or find someone who does have that expertise to create kind of a next generation company. I'm kind of curious from your perspective as someone who obviously is, technical in that way. What would you recommend for, business-minded folks who want to partner up with someone like yourself to build something like this? What advice do you have for them to finding someone in a successful partnership like this?
Yeah, sure. I think in some ways my advice here might be generic with the general trope of how do I find a technical co-founder? I think some of these problems are like accentuated by the fact that I think some of the technical domains in biotech or more generally deep tech companies are deep enough that the joking Paul Graham tongue-in-cheek solution of, well, just become an engineer might not be quite as readily tractable. So I'll sort of defer to all the other salient points. I think for the business operator, it has to start with some level of humility, recognizing that there are going to be decisions in the company that you probably aren't going to be the best person to make. I think depending on what sort of domain you're entering to, the general frame, the most often place I see this is someone who's worked in software, where iteration cycles are very rapid, feedback is very rapid, often output metrics come very early in a company's life. Transitioning into some harder science like biology, where the feedback cycles are going to be much longer. And you sort of have to acclimate yourself to those changes and become comfortable with them early on, because otherwise you'll end up burning yourself out trying to fight against laws of physics, or burning your team out trying to get them to. I'd say another thing that is important is over time, you do need to some degree, maybe recalling that old Paul Graham tongue-in-cheek point, try to develop some of the technical expertise. Don't try and be the smartest person in the room. Don't try and necessarily make those technical decisions, but do try to develop enough fluency that you're able to hold your own in conversations. And it's funny in science, if you're working in the field for a number of years, really what a PhD is an apprenticeship working in a field for about 5 years under a master. If you do the same thing as a business operator in a startup, often you can find that you can develop that same level of technical expertise, but you do have to consciously want to do that. So I'd advise that that's probably the right path toward building an organization where you're non-technical, but some of your co-founders are. So I guess those would be my two highest level bits, is like some level of humility, some level of trying to acclimate yourself to the natural cadence of a different industry, and then setting yourself on a path where you're not you're not trying to be ignorant of the field in the long term. You're trying to set up a situation where you can learn and acquire that knowledge. Even if you won't ultimately be making decisions, you can be conversant in them and understand and have conversations with whoever your technical leads are that get both of you to a productive place rather than being frustrating for either end.
Imagine when you had started in longevity, it was a space that, folks always thought was interesting, but wasn't as pervasive as it is in culture. You think about whether it's New Limit or Brian Johnson or Peter Diamandis or Peter Attia, like Andrew Huberman. They're obviously like different hacks and biohacking, whatever. There's all sorts of different methodologies. Curious, how do you kind of think about the impact that the kind of popularization of longevity has had, and even thinking about building New Limit?
Yeah, sure. It's a great question. I think it's funny, despite all of the attention that you noted, I still feel that the amount of attention given to longevity science is like orders of magnitude lower than I would expect it to be naively. Totally. If you told me like every person on earth has some disease and it's called aging and it's going to get every single person one day, I would think everyone would wake up and be like really freaked out by this and want to be trying to research why this is happening as readily as possible. And yet that doesn't seem to be the most common case. Like, sure, it comes up at cocktail parties every once in a while, but if there was a meteor headed toward Earth, you'd expect people to talk about it more. It's sort of the situation we're in.
Totally. Yeah.
So I do think that having that level of attention on the field, getting some popular sentiment, really is helpful for raising the salience of the question of why do we age? Is there something we can intervene on? How can we make people's lives better as a result of understanding this biology? I think there's also another side of the coin too, which is that there's some level of popularization, which unfortunately tends to stretch the truth a bit. People will often make claims that are more hyperbolistic than probably is warranted by the evidence. And that can actually lead to some distrust in anyone who says that they are pursuing trying to understand longevity, trying to build an intervention for it as a medicine. And so I feel that probably the most likely, the most common impact of a lot of popularization that stretches the truth for us is that you have to really try and establish your scientific bona fides right at the beginning of the conversation as a result, to ensure that you are going to be rigorous with your claims. So I think there's both a positive and a negative. I'd say that our general sentiment toward broader popular attention to the company is that we really just want to focus on the problem we're trying to solve, and we imagine the right kind of attention will come when we have solved it. And so we try not pay too much attention to chatter that might occur about the company, positive or negative, or the field, positive or negative, externally.
Yeah, I'm curious, do you face a lot of critique? It seems like, the mission, to your point, is so noble. Like, everyone is affected by this. Extending life seems to be very uncontroversial, but somehow, every argument has two sides of the coins, I guess, or two sides of the coin, I guess. But do you guys face critique or impacted by it at all? Yeah,
I don't think it impacts anyone in the company in a material way, but it is very common. that you'll tell someone what you're up to, or you'll be talking with other biotech leaders, whatever it may be. And the first question is like, is that really important? Do we really want to live forever? And I think people jump immediately to the hyperbolic limit case extent of what might be possible, rather than looking more locally on the lost landscape today and asking, if we could slow the pace of aging by 5%, would that be good? Would that help each of us be happier? Would that improve the human condition? And so I do find I spend a surprisingly large amount of time trying to both level set people with where we are in the field. Like, we're still working, if I can make an analogy, on like getting a rocket to space. We're not at like FTL travel today, considering like the ethics of whether or not we should land on a given planet. And I feel like that's the type of conversation we unfortunately end up in quite a lot. I do think sort of detracts from communicating the mission more effectively. And I think part of that is, again, just driven by hyperbolic claims that are sometimes made, where people imagine the science is a bit further along than it actually is. So I don't think it impacts us too negatively, but I do wish that we could all, as a field, agree on trying to communicate the science a bit more rigorously. With the current state it is today, incredibly exciting, but also early, rather than maybe leading people to jump to conclusions that are a little bit outlandish relative to what we know how to do today.
Fair.
Has there been, I mean, through the process of kind of building New Limit, whether it's the science or whether it's, some of the other components as well, what's kind of surprised you most about, starting this company and maybe even, some of the things that you've learned as you've kind of dug a little bit more from the research perspective?
Mm-hmm. That's a good question. Surprised me most about starting the company. I guess one thing I would say is, this should seem obvious and will seem obvious to anyone who's founded a company. So this is not unique to New Limit or the science, but the leverage and difficulty of building a really amazing team, I think, is something that had eluded me. Something funny about coming up in academia in your career is that you don't realize you're kind of always recruiting with one of the oldest and best brands in the world. If you work at Harvard, it's like your brand is older than the United States, I think, is the often trope that's doled out. And so I think something you fail to recognize is how challenging it can be in the very early days to assemble a team of amazing people to work on a problem, even when you have some benefits like well-known co-founders in my case, or really exciting science in the case of the company. And then the other thing I underweighted was just how impactful it can be when you get a team of the right people together who are all inspired by the exact same thing. I tell people quite often, the thing I'm the most proud of that we've done at the company is actually not any of the science. It's just getting the really amazing people that I get to come in to work with every day to contribute toward this problem together. So I'd say that was probably the biggest lesson for me. It was almost a lesson in degree in kind. It's not that I didn't think this would be hard or that I didn't realize that having really talented people in a team would be impactful, but it's the type of lesson that when someone else says it to you, you kind of nod along and agree. Yeah. And until you've lived it through it, you don't truly interpret what it means. It's like there's a secret language beneath the language that is really challenging. I'd say another surprise to me has been the different languages that are spoken in the basic science domain, in industry, and then even a layer up at the level of sort of company formation and financing more broadly. This is something that even as a scientist in a relatively large organization, I think you don't get enough exposure to. You would benefit a lot from being further exposed to how the business operates, how business decisions are made. And so I think it's been a surprise to me the degree to which those really are separate languages and you have to toggle between tongues as you're having those conversations. I think those are probably the two most salient.
I guess going back to the conversation we had earlier about, consumers kind of hearing a lot of different perspectives about aging and particularly maybe claims that are, exaggerated from where the science is today. What resources, books, people do you recommend consumers who are non-technical, follow for kind of trustworthy information if they're curious about the space?
Oh, that's a great question. I wish I had better answers for you. Unfortunately, a lot of the aging-specific media is a little bit hyperbolic, and so I worry about naming any one particular source as an endorsement.
Sure.
I would say a lot of the primary source research, I think, will get you, it is actually quite approachable, even as a layperson, and will get you a lot closer to understanding the state of where we are today than trying to read summarizations or synopses of it. Maybe if I could recommend one book, there is a relatively old book called Ageless Quest by Lenny Guarente. who was one of the pioneers of understanding how aging worked in replicating yeast. And I think there's a lot of good biology that's covered there, a lot of good history in the field. It's maybe now 20 years old. But other than that, I'd recommend individuals like actually go to the Nature Aging Journal and read some of the most recent publications. They even have a news and views section, which is written for a layperson. I think sometimes people overestimate the degree to which scientific fluency translates fields. And so even for scientists in a slightly different domain, you often find yourself reading the layperson summary. And so I think there's almost a barrier that doesn't need to be there between individuals who aren't necessarily scientists interacting with the primary source material. So I guess that's what I would recommend, is actually go straight to the source rather than trying to read it through a filter.
Love that. And then maybe just to wrap up before we go to rapid fire, we'd love to hear kind of the state of New Limit today. And you guys had some exciting announcements in September, and kind of just looking forward for the next few years. Like, what's on your radar?
Yeah, sure. So we've been really excited. We opened, the company was founded in March of 2022. We didn't actually open our labs until October of 2022. So just here in about a week, we'll be celebrating the lab's first birthday. And so we've been really excited that we've been able to set up some of the technology we alluded to earlier to run these large screening experiments where we test many hypotheses. And so, when we started out a year and a half back, there was some question of whether or not the technology would even work. Would this be possible? On paper, it all makes sense, but on paper, a lot of things make sense. And so it was unclear whether we'd actually get to the other side. And I'm happy to say that today we've been in a position where not once, but a couple times we've been able to run the largest experiment of this kind that the world has done to date. So we set what we believe to be the first record of that kind back in April. We then set another record in July. And so we've been quite excited by how rapidly we've been able to make progress with that technology. I'd say the other thing that's been really exciting for us is that another big open question when we founded the company was whether we would be able to actually use ML models to narrow the search space. We had this hypothesis that perhaps because we have so much information about these molecules we're manipulating, if we saw some number of results, maybe we could start to predict some of the others. And it was honestly unclear if that would exactly work. It all makes sense on paper, but again, so do a lot of things. And we've been really inspired by the fact that even the earliest versions of our models, given some of the data we've been able to generate in-house, are now able to perform those tasks better than anything we've found in the state of the art outside the company, and to do so well enough that we're able to actually start using the models today to already recommend new experiments we're going to go perform. So I think those are the things that have been most salient for us. And then in addition to those advancements on the science, just being able to set up the team to date, we started a year and a half ago as 2 people, all the way up until when we were opening the labs. We were a company of just 3 or 4. And today, depending on exactly when, exact statistics, we're either 20 or 21 people, which, it doesn't sound like a lot in absolute terms, but in terms of percentage growth, I like to joke is 500% annualized. So quite rapid. And we've been really happy that every single person we've recruited has been really a tremendous contributor to the team. So I'd say those are really the highlights of where we're at today. Looking forward, within a couple of years, we're hoping to be in a place where we can actually demonstrate recovery of function that's lost in immune cells with age. And we think that'll be a really big moment for the field and for the company to really prove out this technology and this general therapeutic approach. So hopefully that gives you some grounding on where we're at and where we hope to go.
Absolutely. Lyra, do you want to kick us off with rapid fire or close us out, rather?
Absolutely. Jacob, these are meant to be answered in 1 sentence or less, and we'll start with the founder you look up to most.
Ooh, okay. I said John Marganor in another setting recently, who founded Alnylam, but I'll give you a different answer and say Josh Boger, who founded Vertex.
Book that most changed your life.
Billion Dollar Molecule by Barry Worth. It's the first book I read that told me that drug discovery is an action movie.
Love that. Which action movie?
That's a good question. It's not quite Bond, but I'd say it's the first book I read that told me that drug discovery could be a fast-paced, really exciting endeavor to spend your life on. I think I had previously imagined it as relatively dull, a bit more like one really long montage scene in Good Will Hunting where he does math. Totally, and I came to learn that it was a collaborative practice where many people were trying to work together on science. Maybe action movie is not the right word, but much more Apollo 13, rapid problem solving, collaborative interaction, rather than solo study of some textbooks alone in a room.
Very cool. What job would you want if you couldn't be a founder?
I'm going to cheat and say just IC scientist. I miss doing technical work all day. I would very readily go be a scientist in a different setting.
Yeah. Do you have a favorite account? It can be a newsletter, Twitter account that you follow, anything along those lines that.
Sure. My highbrow take would be The Diff by Bern Hobart is a really great newsletter on finance and business and tech. My lowbrow take would be there's a Twitter account called Goose Data, which is just biotech memes, and it's amazing.
Yeah, the diff. I mean, he predicted SVB before it happened. So
Bern Hobart may have caused SVB.
He also may have caused it.
Unclear.
Yeah, I mean, he had that article that came out in February that SVB is screwed, and I think every like VC just read that article, and it might have caused it, or January, or whatever it was. What was your first entrepreneurial endeavor? It could have been like a company idea or initiative or anything along those lines.
Yeah, sure. This is definitely in the category of bands that never left the garage. When I was in college, I was working on a software company for basically outpatient clinical monitoring. Never got anywhere. I think I still own the domain. That might be the one legacy.
Love it. And it can be either in your field or not. What's a mega trend that you're extremely excited about that you think most folks are underappreciating?
Underappreciating is hard. I would actually still say the falling cost of DNA reading and writing, so sequencing and synthesis. This is really like the Moore's law of biology, and it's been going for about 20 years, but we still, in many cases, are limited in the hypotheses we can test by how much we can sequence for a given budget. We find ourselves running up against a cost barrier, not a theoretical or conceptual barrier. And so I think as that trend continues to advance, and importantly, as writing starts to catch up with reading, then we're going to come into a place where a lot of the science will be more limited by the cleverness of the questions we can ask rather than the constraints of execution. And so I think that's probably one that 20 years from now, I will still think is underrated.
Very cool.
Jacob, yeah, as a layperson, who actually learned so much from our conversation, really, really appreciate the time. You have a really interesting ability not only to like understand things at a deeply technical basis, but also to explain them to, again, the two lay people like Steph and I. Not speaking for her, but really
I'm absolutely a layperson. Yes, thank you, Jacob. It's been awesome.
Yeah, thank you guys. Really fun conversation. Appreciate the time.